Knowing the edit distance between two strings is important, but it turns out not to be sufficient. We often need something more, which is the alignment between two strings. We want to know which symbol in string X corresponds to which symbol in string Y. And this is going to be important for any application we have of edit distance, often from spell checking to machine translation, even in computational biology. And the way we compute this alignment is we keep a backtrace. A backtrace is simply a pointer when we enter each cell in the matrix that tells us where we came from. And when we reach the end, the upper right corner of our matrix, we can use that pointer and then trace back through all the pointers to read off the alignment. Let's see how this works in practice. Again, I've given you the equation for each cell in edit distance. And if we put in some of our values that we saw earlier, I'll start by putting in some values. So all right, so we can ask, how did we get to this value 2? 2 is, we pick the minimum of 3 values. We could either take, so 2 is the distance, this 2 here is the distance between the string I and the string E. And we got that by saying it's either the alignment between nothing and E plus the insertion of an extra I. So that's distance of 1 plus 1 is 2, or 0 plus 2 is 2, or 1 plus 1 is 2. So we had 3 different values. So if we were asking which minimum path did we come from, really they're all the same. We could have come from any of them. And that's going to be true for this value 3 as well. We computed it as the minimum of 2 plus 1, 1 plus 2, or 2 plus 1. So this could have come from here, here, or here. And similarly, that's going to be true. I didn't work out the arithmetic for you, but it's going to be true for this cell too. You can work it out for yourself. Here we have a difference. So the distance between INTE and E, we could compute that by taking the distance, what it cost us to convert INTE to nothing, and then add another insertion for E, but that would be silly because 4 plus 1 is 5, and there's a cheaper way to get from INTE to E, and that is that it cost us nothing to match this E to that E. So our previous alignment between INT and nothing, we can add 0 from 3 to get a 3. So the minimum path for this 3 came from that 3. So while in some cases a cell came from many places, in this case it unambiguously came from this previous 3. And so we're going to do this for every cell in the array, and the result will look something like this, where we have for every cell every place it could have come from. And you'll see that in a lot of cases any path could have worked, so this 6 could have come from any place, but crucially this final alignment, this 8, that tells us the final edit distance between intention and execution, our traceback tells us it came from the best alignment between intentio and executio, which came from the best alignment from intenti, from executi, and so on. And so we can trace back this alignment and get ourselves alignment that tells us that this N match this N, and this O match this O, and so on. But maybe here we have an insertion rather than a clean lining up. Computing the backtrace, very simple. We take our same minimum edit distance algorithm that we've seen, and here I've labeled the cases for you. So when we're looking at a cell, we're either deleting, inserting, or substituting. And we simply add pointers. So in the case where we're inserting, we point left. In the case where we're deleting, we point down. In the case where substituting, we point diagonally. And I've shown you that arrows on the previous slide. So we can look at this distance matrix and think about the paths from the origin here to the end of the matrix, and any non-decreasing path that goes from the origin to the point NM corresponds to some alignment of the two sequences. An optimal alignment then is composed of optimal subsequences, and that's the idea that makes it possible to use dynamic programming for this task. So the resulting of our backtrace are two strings and then the alignment between them. So we'll know which things line up exactly, which things line up with substitutions, and then when we should have insertions or deletions. What's the performance of this algorithm? In time, it's order nm because our distance matrix is of size nm, and we're filling in each cell one time. The same is true for space. And then the backtrace, we have to, in the worst case, go for, if we had n deletions and m insertions, we'd have to go n plus m. We have to touch n plus m cells, but not more than that. So that's our backtrace algorithm for computing alignments.